Let me introduce myself. I'm Clemens Hammerer and your chair for today. I welcome you all to the joint colloquium of the Collaborative Research Center TQMAT of the University of Hanover and the virtual seminar on precision physics and fundamental symmetries. Our esteemed guest today is Professor Lieven Vandersypen from the Delft University of Technology, who is a pioneer in the realization of quantum computing. Let me introduce Professor Vandersypen to you. He received his PhD in electrical engineering in 2001 from Stanford University. And in his PhD work, he implemented various quantum algorithms using as quantum bits atomic nuclei in a molecule. In particular, he demonstrated Shor's quantum algorithm for finding the prime factors of the number 15. After his PhD, he moved to Delft University of Technology as a postdoc and was appointed Anthony van Leeuwenhoek professor there in 2006. In 2014, he was one of the founders of QTech, a mission-driven research center for quantum computing and quantum internet, whose research director he is since 2020. In 2017, he was co-director of the Kavli Institute for Nanoscience in Delft. For his work and achievements, he received an ERC starting grant and an ERC advanced grant. In 2008, he received the Nicholas Curti Science Prize awarded by Oxford Instruments and the Young Scientist Prize of the International Union of Pure and Applied Physics. In 2015, he received a Dutch SiGe Fellowship to study quantum simulation with quantum dots. And in 2021, he received the Spinoza Prize, which is the highest scientific award in the Netherlands. We look forward to your talk and to hearing the latest about your research towards large-scale quantum processors. Please, go ahead.
Okay, well, thank you very much, Clemens, for this very kind introduction. And yeah, thank you also for the invitation to speak at this combined event virtually. Yeah, so it's always fun to speak about this work, and when I think about the motivation and you know where we fit into this worldwide picture or this picture of worldwide activity on quantum computing, I like to start by showing these images of the first transistor, right, going back to 1947, which remarkably led less than 10 years later to commodity products that people were willing to pay for and that had real value, right? At the same time, these products like transistor radios, they were made by hand soldering together transistors with capacitors and resistors and other elements. And it's clear that, you know, by brute forcing these methods, you can only get so far. You know, there's only so much complexity that you can handle. And that really changed, of course, when the integrated circuit was invented in 1958, which has, of course, enabled processor chips and memory chips with an enormous complexity nowadays, you know, having billions of transistors all on the same chip and working together and driving the information revolution. So if we take this as a starting point and then look at quantum computing, you know, even though today's computers are enormously powerful, the promise of quantum computing is that there will be applications, you know, ranging from the energy domain to health security, where quantum computers outperform classical computers, even the best supercomputers, in real world problems. It's real, you know, complex mathematical physics problems and so forth. But the challenge in doing so is that, given the fact that quantum bits are not perfect and that we need to correct errors faster than they occur, and given that this brings along with it an enormous redundancy in the number of quantum bits using quantum error correction, quickly we're talking about millions of quantum bits, millions of qubits to do something useful. And so, whereas there have been amazing, really impressive experiments, such as the ones from Google or USDC, for instance, with superconducting qubits, demonstrating that the complexity of those quantum processors already surpassed that of supercomputers, but it surpassed it in a very narrow sense. There was a random sequence of instructions implemented or ran on these processors, and of course a random sequence of instructions gives you a random outcome, and that's not very useful. The only thing is that a supercomputer had trouble or was no longer able to verify the outcome because it just got too complex. Now, the big question that drives me is to ask, how can we go from such demonstration experiments, impressive as they are, to a device that can really, in a practical sense, solve problems beyond the reach of supercomputers, that can solve problems beyond the reach of supercomputers that we're interested in, that are relevant, that have applications. So this is, of course, the million-dollar question, and there's a lot of hard work around the world trying to answer it. Pushing through with superconducting qubits, or whether it's trapped ions, as some of you are familiar with, or other techniques. But I would argue that if your starting point is to isolate individual electrons on semiconductor chips using technology that very much resembles the transistor, the semiconductor technology of today, that really is a powerful starting point for scaling. And so in this picture, you would imagine the spin of one electron acting as a quantum bit, and individual electrons being stored in what we call semiconductor quantum dots. For instance, Rolf Haug at Hanover has been working on this for many years, and so you may be familiar with these systems. Let me just explain the cartoon here. In this case, we actually start from the analogy of a transistor where there is a source reservoir or a source contact and a drain contact. Normally, you would have a single gate covering the channel connecting the source and the drain. In this case, there are several gates separated from each other. The gates in orange actually define a channel, and then the gates in blue will accumulate electrons in the channel, but they will all be biased slightly differently, such that along the red dashed lines, you can create potential landscapes like shown here at the bottom. Right, so there are local potential minima. In each of these local potential minima, which we call quantum dots, we can isolate one single electron. That electron can be hopping, can be tunneling between this tunnel barrier from one quantum dot to the neighbor, or electrons can tunnel in from this reservoir to the quantum dot, or can tunnel out, and so forth. But in the regime where we operate them as qubits, we'll have one electron in each of the quantum dots. Now, in most of the experiments that we do in my group, the channel is not just in the silicon next to the silicon oxide or high-K dielectric. It's actually a buried silicon quantum well, separated from the surface and the dielectrics by a 30 nanometer silicon germanium layer. The reason is that if you bury the silicon quantum well and have some distance to the surface and the dielectrics, then you also create distance to the surface traps and defects in the dielectrics, and so that will give you a cleaner potential landscape. The heterostructures that we're using in our work are nowadays all grown by Giordano Scappucci, a colleague at QTech, who is an expert in growth of these materials. So, based on structures made in a slightly different way, but conceptually similar, our community has, I would say, demonstrated one by one the basic elements, the basic building blocks that you would need to think of such quantum dot systems as quantum processors. So basically, for some of you may have heard of the DiVincenzo criteria that were implemented, and they were implemented for the first time in gallium arsenide gate-defined quantum dots. I already mentioned that we're able to isolate individual electrons in each of the quantum dots. In 2004, we showed for the first time that it's possible to make an electron leave the dot or stay on the dot, depending on its spin state, using the Zeeman energy difference between the two spin states. And then simultaneously, using an external charge detector placed next to the quantum dots, we would record whether that charge stayed on the dot or whether the dot was briefly empty. And so in this way, we call this spin to charge conversion. In this way, we can actually infer what the spin state was by probing the charge occupation of the quantum dots. So that's a widely used technique nowadays. There are variations of it. but it's always this converting the spin, which is hard to measure directly, to measuring individual charges, which can be done with good accuracy. And of course, at the Precision Institute, you're experts at this. So then in 2005, the Harvard group demonstrated for the first time the coherent evolution of electron spins in quantum dots by showing that if you allow the two electrons, or if you allow electrons from neighboring quantum dots to overlap a little bit with each other, you allow their wave functions to overlap, for instance, by lowering the potential barrier between them. Then on the spins, an exchange interaction will act, and the exchange interaction will literally exchange the state of these two spins, right? The next year in Delft, we demonstrated that we can perform magnetic resonance on a single electron spin, applying an AC magnetic field on resonance with the spin transition. We can drive spin rotations, Rabi oscillations. And in fact, the year after, we showed that also with AC electric fields, we can drive spin rotations. Electric fields normally don't talk to spin, but they do here because of the spin-orbit coupling. But then the big obstacle in gallium arsenide was that the coherence time, the dephasing time T2 star, was just a few tens of nanoseconds. And the reason is that all the isotopes that exist of gallium and arsenic carry a nuclear spin. These nuclear spins, despite the low temperatures and magnetic field, are randomly oriented, and through the hyperfine coupling have a random effect on the electron spin that quickly dephases it. So I have to say, some 10 years ago, I got a bit pessimistic, by this observation, pessimistic about the prospects for using semiconductor quantum dots for quantum computation. But this pessimism changed into real optimism when our community was able to make the step to silicon. Actually, it was known from the beginning that if we could make quantum dots in silicon, it would be real advantageous, because only 5% of the atoms in silicon have a nuclear spin. And in our group, we showed that this gave a 100-fold increase in T2 star, so a few microseconds instead of tens of nanoseconds. And then the Dirac group, for the first time in 2014, showed that in isotopically enriched silicon-28, the coherence time or dephasing time is extended by another factor of 100. So altogether 10,000 times longer lived spin coherence in purified silicon-28 compared to gallium arsenide. And the silicon, purified silicon-28, it's actually available. It's not even exceedingly costly. And so this quickly also led to a single qubit control with very high fidelity, 3 nines of fidelity, in some cases approaching 4 nines already. In these cases, actually, the drive or the spin rotations are driven again by an AC electric field. But then, in silicon, the spin-orbit coupling is quite weak, and so there was artificial spin-orbit coupling introduced by having a piece of cobalt, a piece of a micromagnet placed on top of the quantum dot. And this piece of cobalt, its stray field produces a local magnetic field gradient at the quantum dot location. And you can imagine, if you use an electric field, an AC electric field, to wiggle the electron back and forth in this magnetic field gradient, the electron will experience an AC magnetic field. And if you do this at the right frequency, you can drive spin resonance. Also several years ago, we could take the system to 2-qubit control, and we had fun programming some of the well-known quantum algorithms that you can run on 2 qubits, Grover and Joyce-Jozsa. And that was fun, actually. It was for me going back to my NMR days that Clemens referred to in the introduction, where we were programming nuclear spins and running quantum algorithms. So based on these advances, with several colleagues in the field, a year or 5 ago, we described or presented a vision for what a scalable spin qubit processor, semiconductor processor, might look like. And in our mind, this will contain the following elements. First, obviously, there will be qubit registers. We envision that they will not be one-dimensional, but two-dimensional, or perhaps 2 by n, I don't know, but not just one-dimensional. And then we also envision that the size or the number of qubits that we can have in such a monolithic register is probably limited. We'll have to see, you know, how far we can push this, but it's probably limited. And therefore, to scale beyond this size of what's convenient inside a single register, we then envision having many copies of such a unit cell all on the same chip. So the entire image here is one single chip, copies of this unit cell on the same chip. And these copies, these registers, will be connected to each other with quantum links, so that you can create entanglement, you know, across the full system. And furthermore, what we envision is some classical electronics integrated also on the same chip to distribute signals and thereby overcome the so-called wiring bottleneck, which is that, you know, we may be able to bring a few thousand wires or signals to a chip, but millions of wires to a chip, that just doesn't seem feasible. So you need ways to distribute a limited number of control signals, you need a limited number of external control signals coming in, and then distribute them over the chip with some onboard electronics. So this is the vision, and what I'd like to tell you about in the remainder of the talk is first our progress in making better qubits, in particular show that we can now also achieve high-fidelity 2-qubit gates. I'll show you process in scaling of these local registers. I'll show you progress on the coherent quantum links that will connect the registers. And finally, some results of collaboration with Intel, where we bring in industry technology to help scaling. So the 2-qubit gate here, I mentioned it before, right? It arises when you allow the wave function of neighboring electrons to overlap, and when you do that, you get a Heisenberg exchange Hamiltonian shown here at the top. But because of this micromagnet that I mentioned before, the Zeeman energy, but you know, on neighboring quantum dots will be different from each other. That means that you know, the spin flip energy will be different for neighboring spins, and this actually suppresses the flip-flop terms, the x and the y terms, which would like to flip-flop the state of electrons in neighboring dots. And when these terms are suppressed, what you're left with is the ZZ term in the Hamiltonian. That's an Ising Hamiltonian. And the experts will recognize what this Hamiltonian basically means. It means that, for instance, the energy of the anti-parallel spin states shifts downwards compared to the energy of the parallel spin states. And you can actually use this to perform 2-qubit gates in two ways. The first is to activate this coupling so that these anti-parallel levels are pushed downwards. And when you do that, then the resonance frequency for driving the first qubit here will be different depending on the state of the other qubit. So this transition in yellow and the one in red will no longer have exactly the same energy. They'll be slightly separated from each other. And by applying a narrowband drive, you can therefore rotate a single qubit conditional on the state of its neighbor. So that gives you a conditional rotation, a C-rod. And the Dirac group 3 years ago achieved a 98% fidelity in this way. In our group, at the same time, we achieved a 92% fidelity on the C phase. And in the C phase, what you do, you slowly turn on this coupling that pushes down the anti-parallel levels, and then you switch it back off. And when you do that, the anti-parallel spin states will accumulate an extra phase, and that basically means that you get a controlled phase rotation depending on the state of your control qubit. Your target qubit will precess a bit faster or more slowly, and thus pick up a different phase. That's the C phase gate. So 98, 92, you know, these are good starting points, but we really want to push this well beyond 99%. While 99% is not a sacred number, it's seen as the typical error threshold that you need to surpass in order to achieve what we call fault tolerance, in order to to remove errors using quantum error correction faster than they appear. And so we worked hard to exceed this threshold. We still use the conditional phase approach in order to ensure adiabaticity. We tailored the the profile with which we switched or activated or pulsed the gate voltage. So to do this gently. Furthermore, we operated at the so-called symmetry point. It's a sweet spot where to first order the C phase evolution is not sensitive to charge noise. And furthermore, we performed a procedure called gate set tomography. It's a known procedure to collect basically all the information that there is to have about the quantum process. And using this information, we were able to improve on our calibration. And so by the combination of these three methods, we were able to reproducibly get fidelities well above 95%, up to 99.65%. Other work reporting fidelities above 99% from the Terucha group was published in the same issue of Nature last January, alongside related work from the Morello group, where instead of using electron spins in quantum dots, they used nuclear spins attached to phosphorus donors as quantum bits, but also in silicon. So I think this is this is a good step for the community that several groups now have shown that it's possible to surpass this 99% fidelity on the 2-qubit gate. We actually had fun also using the high-fidelity gate set to implement another quantum algorithm, in this case, a variational quantum eigensolver algorithm for estimating the binding energy of a hydrogen molecule. Similar experiments had been done previously with trapped ions and superconducting qubits, and we actually get really nice results here for the experts. Not quite yet reaching chemical accuracy, but still, very good agreement with what you expect. So, okay, having good control over a two-level system, that's a good step, but obviously we need to show that we can get control over more qubits that we can scale. And in the past years, there has been progress along this front. The PETA group, for instance, built a 4 quantum dot array. In this case, they only loaded an electron in one of the dots at a time and were able to rotate it. But then the Veldhorst group, my colleague Menno Veldhorst at QTech, showed in a 2x2 array of quantum dots. In this case, it's a germanium quantum well instead of a silicon quantum well. They showed full control of those 4 spins. The Terucha group showed entanglement of 3 spins in a linear array of silicon germanium. And here I will show you work on a 6-qubit array in silicon germanium. So you may recognize the pattern that I've shown before. So you've got these screening gates that define a channel in red, and then in blue and in green are the gates that locally form this potential landscape with 6 potential minima at the locations of these 6 yellow circles. Here are these ellipses represent larger additional quantum dots. These are our external electrometers. And then in kind of gold color here are the contours of the cobalt micromagnet that sits on top. With this system, we are in this experiment, we actually not only demonstrated 6-qubit control, we also introduced several new elements, although perhaps for the sake of time, I'll gloss over that. It's initialization by measurement, things like that, quantum non-demolition measurement, etc. But maybe I'll just skip over this and instead show you that we can really control very well the spin state of each of the 6 electrons. You see the beautiful Rabi oscillations. I should point out these are not simultaneous Rabi oscillations. The electrons are there all the time, but we rotate 1 spin at a time. If we characterize the gate fidelities 1 at a time, it's very nice gate fidelities around 3 nines, just below, in one case, in 2 cases just above 3 nines fidelity across the 6-qubit array. And furthermore, the visibility is actually quite good. So these oscillations are not normalized; they're just raw data. Visibility is around 96, 97%. If you're thinking in terms of fidelity, right? If you have a fidelity on the initialization of 99% and a fidelity on the readout of 99%, then your visibility would be 96%. So that kind of puts it in perspective. It's quite good initialization and readout across the 6-qubit array. And here we show that also the 2-qubit control is actually quite good. We get Bell state fidelities that are consistently larger than what we used to get on just a 2-qubit device several years ago, but now we get it on a 6-qubit device. So returning to this vision, right? So I spoke about improving the fidelity of the control and extending the local registers. Let us now turn to the quantum links. And there are several ways for building the quantum links. There is one, and I'll mention it here. There is one that I think is actually very powerful, but I won't expand on it in this talk, which is one where you shuttle electrons through a channel from one register to another in such a way that you preserve the spin state. This actually bears some resemblance to the devices used for current standards, where charges are controllably passed along, and I think this could also form a basis for such quantum links. But let me instead show you some results where the quantum link is given by a superconducting resonator, similar to the ones used by the superconducting qubit community. The superconducting resonator will be, well, at low temperature, it will be in the regime where there are no photons. But when we bring the qubit, the spin splitting, on resonance with the frequency of the superconducting resonator, we see that the two actually repel, that an avoided crossing exists. And so the electron spin interacts with the microwave photon in the resonator, and the spin and the photon hybridize. You get this avoided level crossing, and the separation between the two levels was larger than both the decay rate of the resonator and faster and larger than the dephasing rate of the spin. And so that means that we've reached, and this is from 4 years ago, reached a strong coupling regime where a single microwave photon is strongly coupled to a single electron spin, with similar results from groups at Princeton and ETH. In recent work, we have coupled 2 sets of quantum dots to the resonator. So the resonator in this case is just a piece of superconducting wire, and there are reflection points at the end, and so there's a standing wave in the middle, or that forms. And so at one end of the resonator, we have this double quantum dot. At the other end, we also have a double quantum dot. And now the question will be, can we couple the spin on the left quantum dot to the spin on the right quantum dot, which is 150 micrometers away, or 200 micrometers away. And the first step to do this is to go back to this strong coupling regime on the left and on the right, and we achieve the strong coupling regime on both sides. So that's a good starting point. You see it again here in the middle, the avoided level crossing larger than the line width. The next step, and this was done also in the PETA group 2 years ago, the next step was to simultaneously tune to the strong coupling regime on the left and on the right. And as expected, the avoided level crossing was enhanced by square root of 2. This is the collective enhancement by square root of n that you get if n two-level systems are coupled to the same resonator. In this case, n is 2. So it's enhancement by square root of 2. But then in the next step, and this was just published, we tested whether also a direct spin-spin interaction could be seen whether we could see a avoided crossing between the two spin states by bringing them off on resonance with each other, while both being detuned from the reservoir, from the resonator. So this is in the so-called dispersive regime. And the way that we manipulate separately the two resonance frequencies of these two spins is by varying the angle of a magnetic field and by having two micromagnets sitting on top of one quantum dot and the other quantum dot at an angle from each other, such that the Zeeman energy changes by a different amount in one on one location versus the other. And so when we bring both of them on resonance with each other and let them interact dispersively with the resonator, we saw, as we hoped, an avoided level crossing, which was larger than the spin dephasing rates. So we've reached here the so-called strong coupling regime between the two spins. You will notice that the upper branch here of this avoided level crossing is not very visible, and that actually is expected. That's a dark state, so it shouldn't be very visible. But yeah, this is again a good step. What we're doing at the moment is to see if we can now use this interaction at a distance to also in the time domain see a coherent evolution, a 2-qubit gate between distant spins on the same chip. So that's still ongoing. A interesting fact, when we were doing these measurements, in some of the measurements, well, I didn't point it out specifically, but you're basically doing spectroscopy of the spins, right? And the line width, we noticed in many of our measurements was broader than what we had expected for the spin line width. And furthermore, the line had an asymmetric shape. And we were initially puzzled by this until Patrick, the postdoc who was doing the experiment, realized and pointed out that we should have expected this. This is actually well-known physics from the superconducting qubit community. What's going on here is that, again, because of the strong interaction between the spin and the resonator and the other spin, compared to the relevant decay rates, our spin resonance frequency actually becomes sensitive to the number of photons in the resonator. And so we're here doing a measurement, a quantum non-demolition measurement of the photon occupation in the resonator. So here's the main dip for the spin resonance, and then you see that it's shifted if there is a single photon in the resonator. Admittedly, the dip for 2 photons is not really resolved, but at least in the beginning, the first 2 are clearly resolved. So this effect, it's equivalent to an AC Stark shift, where a qubit sees its frequency shift by an AC drive, but the AC drive is now coming from a single microwave photon. So then, as the final piece of this vision, let me comment on where we're at integrating the electronics on the chip, and also where we're at in advancing the technology for fabricating the quantum bits in such a way that it really makes use of all the know-how and power of the semiconductor industry. And in this context, more than 7 years ago, I initiated discussions with Intel that resulted in a long-term collaboration where we have worked together, bringing together our quantum dot expertise and their semiconductor manufacturing expertise to see if it were possible to fabricate quantum dots using all optical lithography, all the techniques used to fabricate transistors and integrated circuits. So for many of you will be familiar with this, right? So it's etching, it's no lift off, it's chemical mechanical polishing. So really, all the techniques used for transistor technology come back in the work here where quantum dot arrays are made. And the quantum dots are defined in fins, just like conventional transistors in modern Intel chips are defined in fins. So these are silicon fins embedded in dielectrics. And then there is the electrode running on top. In this case, there are 2 fins side by side. And on top of each fin, there are multiple gates, right? So you see a single fin here, another fin there. Each of them has multiple gates. And if you look at the TEM cross section of the gates, you see here a beautiful gate stack. The gates are deposited in 2 layers. The G2s, well, the even numbered gates are deposited first, and then in between the odd numbered gates are deposited. Those familiar with this type of advanced manufacturing procedures will recognize the extra metal on the chip that serves no function as far as the quantum bits go. It's just there to have a somewhat uniform density of metal on the surface, so that chemical mechanical polishing becomes possible. Yeah, what it results to is these beautifully controlled gate stacks. For comparison, here is a similar image from a device from our group, and we have an excellent clean room as university clean rooms go, but the techniques are just different, and the outcome is just no comparison in how well controlled the structure is. So what does this translate to? It translates to a almost 100% yield, defined as the device turning on at room temperature, all the gates responding. We had at the university, on our best occasion, we had a 50% yield. Usually it's 10, 20%, often it's 0%. But so on a full wafer scale here, so 98% of the devices were fully functioning. And furthermore, the spin properties are quite comparable to those, or on the better end of those reported in the literature, meaning that all these, I would almost call them harsh processing conditions and all the restrictions of the optical lithography have not stood in the way of very respectable T2 stars, T2 CPMGs, and gate fidelities. In terms of integrating some conventional classical electronics on the chip, we haven't done that yet. But what we have done, also in collaboration with Intel and with our colleagues from electrical engineering at TU Delft in QTech, is to design a cryogenic chip, to design a CMOS chip, I should say, designed for cryogenic operation and to generate control signals and modulate control signals. And it's actually, I've been really impressed with how powerful this little chip is. It's just a few millimeters on the side, and it largely replaces a commercial instrument that we use for vector control, a commercial vector source. It's largely equivalent to that in its functionality, and it's multiple channels. Each of the channels can be amplitude modulated, can be phase modulated, multiplexing capabilities, and so forth. It's really quite powerful, so we actually did a direct comparison in the gate fidelity reached between the commercial vector source and this little chip. We had a microwave switch in the cold so that we could connect the same device without warming up to either this cryogenic chip or the commercial instruments, and we got the same 99.7% gate fidelity. So that was limited by the qubits in this case, not by the control. And we also demonstrated the functionality of this chip by programming 2-qubit algorithms on it. Of course, if the vision is to bring this cryogenic chip onto the same, if the vision is to bring cryogenic electronics on the same chip as the qubits, then the qubits are going to heat up, right? And there will be power dissipation. And so my colleague Menno Veldhorst has shown a couple of years ago, or has tested how much coherence and gate fidelities are compromised when going to low temperature, to higher temperature. We call it hot qubits. It's kind of tongue-in-cheek, right? It's comparing to 1020 millikelvin. A Kelvin is high, and he got 99% single qubit gate fidelities. In that case, 86% 2-qubit gate fidelity, but with a lot of room for optimization. This is just the first pass at this high temperature qubit control. And so that's certainly something that we're going to look at further to see how much we can allow the chip to heat up without compromising too much the qubit properties and fidelities. So coming to the end here, you know, I've shown you results along 4 research lines in our group. On the one hand, over time, trying to improve the degree of control over the gates and the initialization and the readout, exemplified by the 99.6% 2-qubit gate fidelity. Our drive to increase the number of quantum bits that we can control, as shown here in these 6-qubit circuits. Test ways for coupling, well, for forming quantum links that can connect quantum registers that are some distance from each other on the same chip to each other with a quantum link, preserving quantum coherence and allowing entanglement to be distributed. And finally, I've shown you our efforts together with Intel to fabricate in the Intel clean rooms qubit chips that with amazing uniformity, excellent yield, and I would say respectable qubit properties, as well as fabricating in their clean rooms cryogenic control chips to move down the path of bringing the classical and quantum components together on the same chip. So I would say that, yeah, you know, one piece at a time, we are really testing and implementing these ideas. More and more will bring more of, well, over time, we'll bring more and more of these elements together into the same experiment. And so certainly we have a long ways to go, and we're still very far away from, let's say, a quantum supremacy experiment on this system. But I think we're on a good trajectory. I think that the long-term prospects are good, and we'll certainly do our best to make it happen and to take the next steps. Before closing, let me also advertise our Quantum Inspire system. This is an online platform, inspired, we're pioneered some years ago by IBM, but this is our own online platform where you or anyone can play with real qubits. In our case, it's both semiconductor qubits and superconductor qubits. It's a non-commercial offering, the first one in Europe, and I certainly invite and encourage you to use it. We also use it in our teaching. For instance, we use it in outreach and so forth, just the European version. Importantly, this is teamwork. Here is a Corona-compatible group picture from last summer. Many people have contributed to this work over the years, not only from my group, but also the materials from Giordano Scapucci, the work on the related work on spin qubits from Manuel Veldhorst at QTIC, collaborators from Wisconsin and ETH on the materials, many collaborators on the theory, the team from Jim Clark at Intel, the cryogenic CMOS team at QTIC and at Intel. And so, yeah, this is really teamwork. I'll thank all of them and thank you for your attention.